I'm going to be explaining how blood flows through the heart and body in terms of pressure. I'm also going to be explaining the pressures that are involved in perfusion. And lastly, I'm going to describe the short-term neural control of blood pressure in regards to cardiac output and total peripheral resistance. I'm going to start with that one actually. So first, let's go over the short-term blood pressure regulation. So we have chemoreceptors and baroreceptors in our body. These are what regulate and monitor the pH and oxygen levels inside of our blood. So we have chemoreceptors that are located kind of mostly in our neck, and these measure the pH and they tell the heart whether to beat faster or to beat slower. So let's draw this out and understand how all this ties together. So first, we have our receptors. Is that big enough for you to see?
I can't see it with the glare.
Okay. Well, while I draw it and explain it, you might not be able to see it on the video, but we'll zoom in at the end and show you. But drawing it just helps me to explain it. So we have our receptors, and our receptors include chemoreceptors and baroreceptors. Alright, so these are what monitor the pH and the oxygen inside of our blood. So first, signals are sent from there across a sensory neuron that says, hey, we've got plenty of oxygen, or hey, we've got too high of a pH, or so on. So the sensory neuron goes to the medulla. And from the medulla, we go to the cardio-acceleratory or the cardio-inhibitory center. So we got the cardio-acceleratory, and we have the cardio-inhibitory. All right, let's get a view of what I've got so far. So we go from the medulla to the cardio-acceleratory or the cardio-inhibitory, and from there, depending on whether it's too high or too low, when I say too high or too low, I'm talking about the pH and the oxygen levels. So from there, these signals are going to travel along to our heart, to the SA node. So if it's coming from the cardio-inhibitory center, then it is going to travel along the vagus nerve, and this is where our ACH comes from. So, and that is the parasympathetic nervous system. And if we have signals coming from the cardio-acceleratory, then those are traveling along a sympathetic pathway. And our sympathetic pathway sends norepinephrine. So the way that this affects our blood pressure in the short term is these all affect our cardio output. So the equation for blood pressure is cardio output times total peripheral resistance. All of this right here affects the cardio output. And that's SA node control. That's what we'll refer to all this as. So next we have total peripheral resistance. So for total peripheral resistance, This includes several things like vasoconstriction, the amount of concentrates inside of the blood, or the amount of substances inside of the blood, whether that's nutrients or gases or anything like that. So in this situation, we are going to be referring to vasoconstriction. So vasoconstriction. So now we're talking about total peripheral resistance and vasoconstriction, and everything here is the exact same for the most part as the cardio output control, except there's only a sympathetic pathway. We don't have a parasympathetic pathway, so there's no inhibitory center, there's only an acceleratory center. And so vasomotor is the center of the medulla that we are sending the signals to, and instead of sending something to dilate the vessels, we only send stuff to constrict them. So whenever we have a reason to constrict them, signals are sent from the vasomotor center of the medulla. Signals go this way to the baroreceptors. And these tell our vessels to constrict. So constrict. And to make them dilate, we stop sending the signals and they dilate. So whenever our vessels are constricted, and the constriction happens in the arterioles. So when constriction takes place, our blood pressure rises. So constriction equals increased blood pressure. Dilation equals decreased blood pressure. And that is how our blood pressure is regulated in the short term. So we have cardio output controlled by the chemoreceptors and the baroreceptors, and the baroreceptors are along the vessels. They send the signals. Basically, they're like the ones that they receive the signals from the medulla to put into place whatever it is they're trying to do, whether it's inhibit or accelerate. And all these signals are sent to the... Next, I'm going to be explaining how the blood flows through the heart in terms of pressure, and we're going to be going over venous return and the different mechanisms that help cause that. So first, let's go over veins. They're low pressure. They rely on the blood pressure caused by the heart pumping to be able to make their full cardiac cycle. Like for all the blood to be able to go from the arteries through the capillaries and back into the veins, we're relying solely on the heart to pump it all the way through. But actually we're not. That's why we have skeletal muscle pumps and we have respiratory pumps. So the way these work is they basically give the veins a circulatory bump along the way, so to say. So first we have our respiratory pump. When we inhale, the pressure goes up and it pushes on the lungs and causes the veins to, like the pressure inside of the veins to rise, and it forces the blood through the veins and back to the heart. And what keeps this from the blood from going backwards is we have valves. The valves make sure that the blood flows in the right direction. So when we breathe in, our pressure in our chest and our abdomen is pushing on the veins and is forcing the blood back to the heart through the veins, not backwards through the arteries. So then we have our skeletal muscle pump. And basically the concept of this is movement causes pressure on the veins, and that forces the blood through the veins to the heart. So the main source of our I guess like the main place where that mechanism is used is in our legs. So when we move and like when we walk, pressure is created inside of our legs, and it forces blood back through the veins and to our heart. So our muscles shorten and the diameter of our muscle increases whenever the muscles are contracted. For example, when I contract my bicep, the muscle is shortening and the diameter is increasing. And this applies pressure on the veins, and it creates a pressure gradient. And it's similar to the respiratory pump, except this is just from muscles contracting. It's not from breathing. So we create the pressure gradient, and the valves make sure that the blood does not flow backwards. We don't need it to do that, or we never get back to the heart and get reoxygenated by sending it to the lungs. So yeah, that's basically how that works. And so whenever we walk, we are forcing blood back to the heart through via a pressure gradient on our veins, and the same with our lungs. When we inhale, we are creating a pressure gradient inside our veins and pushing the blood back to the heart. And luckily we have valves to prevent backflow. So now we're going to go over perfusion and how perfusion works. So perfusion is the movement of oxygen and other nutrients through our tissues from the blood. So we're going to draw this out here. Whereas with osmosis is just the diffusion of water across a membrane. We are actually talking about perfusion, which is the movement of molecules and oxygen, gas, and stuff like that. So I'm going to draw this out here. First, these are going to be our cells. And this is going to be our capillary. So, and then this is our interstitial space. All of this is liquid, and it's called interstitial fluid. Oops. Ooh, I spelled that wrong. Okay, so the way this works is inside of our blood, or inside of our capillaries, is blood. Outside of our capillaries is interstitial space. And I totally spelled that wrong. That's a T. But so from here, we have blood. It's carrying gases. So let's say O2, nutrients, and other stuff. And so we have blood pressure, and then we have osmotic pressure. The blood pressure is going to push these things through the capillaries and into the interstitial space. And so inside of the capillaries, the pressure is the highest. Outside of the capillaries in the interstitial space, the pressure is still high, but it's not the highest. So we'll say higher. So stuff is going to move into the interstitial space where the pressure is higher. And then from the interstitial space, we are going to travel to the lymphatic capillaries. And the pressure is low inside of these. And I'll explain why it looks like this in just a second. So this is a pressure flap. And it lets the blood, or lets liquid come into these. So our lymphatic capillaries, basically, they vacuum up everything, all the liquid that they can, from the interstitial fluid. And then from here, so inside of here is low pressure, and from here it goes to our lymph nodes where filtration takes place. And we'll draw a lymph node as a circle. I have no idea what they actually like. So once it goes to our lymph nodes, then we have flow back to the subclavian, and those are right here in our shoulders. So they're up here, and from there the blood travels back into the veins, which is the subclavian vein, but then it goes back to the heart. So from the lymph nodes it goes to the subclavian, and all that fluid re-enters circulation. So our lymph nodes are actually what do all the filtering and get out all of the nutrients and all that we need for our body. So that is how the perfusion process takes place. But we also need to go over the fact that there is a hypertonic pressure here, and there's an osmotic pressure here. And so our net filtration pressure equals our blood pressure minus our interstitial pressure, minus our blood osmotic pressure minus our interstitial osmotic pressure. So this is going to be hydrostatic, and this is going to be osmotic. So this bind is caused by liquid, this one is caused by molecules. So the interstitial fluid sits between the cells. That's also what causes swelling. And if we're not able to remove if we have too much interstitial fluid, we're not able to remove it from our body, then we are left with swelling. So, and that's lymphedema. And so this is the equation for the net filtration pressure. And both of these are kind of, how to say it, the osmotic and the hydrostatic pressure, they're kind of working against each other to keep it from becoming, or to regulate it, in other words. And so to regulate the passing of O2 and glucose through the capillaries and all that, we have our blood pressure gradient, and we regulate it using the arterioles, the sphincters, and all of these are precapillaries. So let me see. We'll draw this out here. This is going to be this is an arteriole. So when we constrict it, blood pressure goes down. When we dilate it, blood pressure goes up. Okay. So normally when we constrict our arterioles, blood pressure increases, but in this case the arterioles are before the capillaries. So whenever we constrict our arterioles, our capillaries are receiving less blood as a result of that. Therefore, the blood pressure goes down inside of those. But when we dilate our arterioles that are precapillary, then the blood pressure goes up inside the capillaries, even though it's lowering inside of the
inside of the arterioles and, you know, all of our everything else besides the capillaries. So this is called autoregulation, and myogenic regulation is the thing that says, let me write this out. So autoregulation is just the mechanism by which we regulate net filtration pressure. Myogenic regulation is what we use to say, hey, my pressure in my capillaries are too high. I need you to pull back or stop. So hey, capillaries are about to bust. Help us out. And that's myogenic regulation. So obviously we have varying needs of O2 and varying needs of glucose, and the amount of O2 and glucose that we need are largely influenced by whether or not we're working. Cellular respiration is, that's how energy's made, and so just physical activity obviously is going to require more O2 and more glucose for the cellular respiration to take place, therefore, so we can get energy. So if we need more, then our arterioles dilate, and if we need less, then our arterioles constrict. And this is all done by what we went over earlier with our chemoreceptors and our baroreceptors. So all of this, our chemoreceptors and baroreceptors controlling the cardio output, and our total peripheral resistance, all of this relates to each other to control perfusion. So everything is tied into each other. It's all, basically, it's one big unit. But each one has its little differences. So, yeah, that is everything. So, in today's lesson, we have gone over how blood pressure works in the short term right here. And this is through the control of cardiac output and total peripheral resistance. Next, we went over perfusion and how that works, how gases and nutrients and other stuff are transferred from our blood to our body, or to our cells. So actually, one thing that I left off, I'm going over now. All the O2 and the gases and stuff, I just forgot to draw it right, they go into our cells. So that's how it works. But yeah, so we have perfusion and blood pressure regulation, and then we have our skeletal and respiratory pumps, which I demonstrated sitting in the chair. So that is all.